Welcome to the channel where all you gotta do is explain all the issues with the Tesla LDU. So we have a cross-section-ish of a Tesla drive unit that I just kind of drew on a dry erase board just to kind of show the stuff that I'm talking about. I have a list of things that are not necessarily wrong with the drive unit, but definitely not design features that are particularly good. First of which is the water seal. So I think this is the major number one problem on drive units, this LDU drive unit anyway. And the problem is there's a seal right in here. And the reason for that seal is somebody decided that coolant comes in here, it goes this way and goes through all these little cooling channels, you know, it's a labyrinth of cooling channels, and then out the top, and then goes to the inverter to cool the inverter, which in and of itself is wrong. You should cool the inverter first, because that stuff needs to stay cooler, but anyway, that's the way they did it, which, that's fine. The other path it has is to go up to here, and it goes through the center of a shaft that's inside the rotor. There's a drilling in the rotor. And then it comes out, and then out this little, there's a little hose that goes to the top. So that's all fine and dandy, and the purpose of that is to cool the rotor. However, this seal has to spin 18,000 plus RPM at max speed. So it needs to be like a really, well, it's a pretty big diameter. It's almost 30 millimeters in diameter. So you can't just use, you know, a Viton seal or HMBR or something like that, because it won't survive at those speeds. So you have to use a Teflon seal to make it survive at those speeds. Now, if somebody wanted to make the top speed of the car 100 miles an hour, then we could totally do that. But somebody with E in his first name and M in his last name decided that 155 or 162 miles an hour was the top speed. So there's a seal here, and they fail. There's actually several different versions of the seal. There's the original seal that leaked, and then it was redesigned with little pleats in it, so it's a rotational seal, so it seals better in one direction. And then there's another one that seals better in the opposite direction, and that's for the Toyota RAV4 and the Mercedes B-Class, because they basically have the same drive unit with backwards helix gears and parking pawl and some other differences, but the seal is different, and it's a different color. It's anodized red instead of anodized grayish. So keep a lookout for that. And the problem is, if you get rid of this rotor cooling, then your rotor isn't cooled. Now, the rotor is pretty heavy. It's about 45 pounds, so it takes quite a long time to get hot. Unfortunately, it takes quite even longer to get cooled down. But ancillary to that, it's in kind of a confined area. So if the rotor gets hot, the stator gets hot. And this LDU doesn't have great cooling to begin with. So you could probably make it around Laguna Seca, maybe 3/4 of a lap before the motor overheats. So if you did this rotor cooling delete, you probably wouldn't make it 1/4 of a lap before the motor overheated. Now, there's no way to know that the rotor is overheating because there's no sensor in it. But there is a sensor in the stator embedded into this potting compound on both ends here, which we'll talk about a little later. One other problem with doing a seal delete manifold, which I have one right here, and I actually found one that Tesla made and sold to somebody apparently. So it's a thing. It's a cast part. I was not aware that it was ever put on production units and sent to customers. And the reason for that is there was a problem with the large drive units in the early days, which is the bearing discharge problem. So the bearing discharge problem was basically this is a big capacitor, right? A combination of this and this gap and this makes this whole system a capacitor. And then you're exciting it with a frequency drive. So there's a charge that builds up on the rotor, and that rotor has to get rid of that charge in some way. So it discharges, kind of like an electric discharge machine, EDM. And that ruins bearings. Now, when this was designed, they knew that was a thing, so they put silicon carbide hybrid ceramic bearings on this rotor bearing and this rotor bearing. However, there's a spline here that interfaces with the gear, input gear, and these are both made out of, metal. So there's a conduction path through these splines, and then subsequently through this bearing, the 6208, which is a steel bearing. So a lot of the early cars had what's known to the world as milling noise. Not sure who came up with that. I've milled a lot of stuff in my day, and that's not the noise, but that's what they call it. But it's basically caused by the electric discharge through that bearing, and that makes basically it makes a defect in the surface of the bearing race, and then, as you can imagine, it's like a lightning strike hitting the surface, a nice smooth surface of the bearing. And of course, that leaves like a volcano type crater, right? So there's a big hole, and then around the hole there's a big, moat of metal. And then that moat of metal sticking up. So the next time it discharges, that sticking up moat is the first to react, like the closest distance. So that's where it strikes again and again and again, and it keeps having a compounding effect. Not only does it have a compounding effect of lightning strikes, but the ball hits it and bounces. So the ball kind of goes over a jump and then lands a certain distance from there, depending on speed and mass of the ball, square decay over m, blah, blah, blah. So if you run at a consistent speed with a damage on the rotor surface or on the race surface, it's going to make another impact point. And that impact point is when the minimum distance from the ball to the race, because the film thickness, it's going to be a higher load, so the film thickness goes down, and then it discharges more. So you get this series of fluting pattern where the ball is just bounce, 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 and spark, 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 spark the whole time. So this takes 10, 20, 30, 40,000 miles to, depending on how you drive, state of charge the battery, and a bunch of other things. But the early ones had that problem. Now that was fixed in 2015-ish by putting in common mode choke. The problem with the seal delete manifold, which is what was called internally a Tesla, because it deleted the seal, is in order to make EIBD, or bearing damage, not occur, you need basically a two-state solution. You need a common mode choke, and you need some sort of a grounding path other than the bearings that are transmitting load. On the Model 3, there's a 608 bearing with conductive grease in it, and a common mode choke, and that has essentially no EIBD. So, not to worry, Model 3 is fixed. However, the LDU, the solution was to put a choke in it, and while that fixed the problem, it only fixed the problem because the pipe that's inside of the rotor and the interaction between the glycol and that pipe, which is grounded, acted as a ground bearing or a grounding solution. Some people use silver carbon brushes, like a commutator brush. The Nissan Leaf uses that as a solution. But it turns out this accidentally was the rotor grounding solution. So if you get rid of that seal, and you get rid of that, it's, I don't know, 10 inches long or something, it's a big shiny piece of aluminum, that acts as a grounding solution. So I'm not saying you shouldn't put a sealed delete manifold on. There's lots of people making them. Some of them are of pretty questionable quality. But if you do put that on there, know that you fixed one problem, but you potentially introduced another one. So, and the other one is probably a better problem, because what happens is this bearing here, which is the input gear bearing, the 66208, that bearing will get damage, and it will start making a lot of noise. It'll sound like there's a fire engine behind you. And every time you push your foot on the gas, their siren gets louder, and every time you let off of it, it gets quieter. The good news about that is you can pull the drive unit apart, put that new bearing in, put it back together, everything's fine. Whereas if this seal leaks and the coolant gets inside the stator cavity, several bad things happen, right? First, it washes the grease out of this bearing, which you can replace that bearing, so that's not the end of the world. But this is the end turn of the stator. It's potted with a polyester, like a high silica filled polyester for heat transfer. And polyester is very absorbent to moisture. So as that gets more moisture and more moisture and more moisture, and not only does it swell, but it changes the resistance, and at some point it can short out. The other problem is it can get enough in there that it gets through into the inverter. There's no seal between the inverter and the stator area. It's kind of all open. There's like a little piece of paper, to keep frogs or something to jump through, but water can get into the inverter, and the control box is on the bottom and shorts that out and kills your inverter. So putting a sealed delete manifold on might be a good solution. I have one sitting on my desk here that I've been thinking about putting on my wife's car. She has a 2013 P85 with 133,000 miles on it. And that drive unit was in the car when I bought it at 58,000 miles. It is a revised drive unit. It has a choke and better rotor splines and stuff like that, but it's probably really close to end of service life. So I really should put a sealed delete manifold on it soon before I ruin the whole drive unit. But anyway, so this is attached to the rotor shaft, and it interfaces with an internal spline on the input gear. And some of the early ones, pre-2015, the splines were not good. The material wasn't heat treated appropriately, and the spline shape was not appropriate, and there's 6 or 8 problems with the spline. I won't go into them all, but the easiest way to tell if the rotor has the upgraded spline is the early ones had 2 O-rings to seal to the rotor, or to seal to the input gear, and the revised spline has one bigger O-ring. Because those O-rings, there was 2 of them, and they were really little, and they got cut during assembly, so we went to one big one, and that fixed that problem. Another problem with this drive unit is it was originally designed for 380 Newton meters of torque at the rotor, and over the years people wanted it to do more than that, so they just turned it to 11 and 12 and 15 and 18. Anyway, when you do that, things in the chain of links end up being overwhelmed. So the differential is one of them. A couple of problems: the cross pin breaks and the side gears break. Probably 2014, there was a stronger material for the pinion gear, 9310 pinion gear, which helped the pinion gear from breaking, but the pin was the same, so that still broke. Later, 2018-ish, there was a 4-pinion differential designed for it, and that essentially solved the problem. So if you have a newer unit or a reman unit, it probably has all this stuff upgraded, but if you're buying an early unit, be very careful. The easy way to tell when you're buying a unit is if it has an R at the end of the serial number, it'll have like a P15 big long number, and then if it has an R1 or R2, R3, R4, that's how many times the unit's been remanned. So if it has an R5 on it that's been remanned 5 times, you might walk away from that one. If it has an R1, probably okay. And then the P16 would be the year 14 or 12 or whatever it is. One of the other major, I consider it major, and it was addressed on the Model 3, is the stator cooling. All the cooling is through these little channels. So there is conductive paste, essentially, like a conductive grease that's in between the stator housing and the aluminum housing that's cooled. So there's quite a big thermal resistance between the two, which results in the 3/4 of a lap at Laguna Seca before the stator overheats. So there is a sensor embedded into the potting compound, so it will protect itself. But if you want to do spirited driving on a track, or probably be okay on a mountain road, you run on a road and ideas pretty quick on that scenario, unless you don't care about your license. But on a track, it's just, there's not any margin for anything but spirited mountain road driving. Another failure mechanism of this is probably due to the increase from 380 newton meters to 725 newton meters, is the motor mounts, the little rubber bushings. Well, they're actually pretty big rubber bushings, but those rubber bushings fail. Motor's not going to fall out. It's captured, but it'll make a clunky noise when you get on the throttle hard. That's a pretty easy fix, so it's pretty far down on the list, and it doesn't really cause any big problems. Yeah, the next on my list is this cavity here is full of oil, and there's no filter. There is a pump, but the pump's only purpose in life, well, it has 2 purposes, but one doesn't really do anything. So it pulls oil out of the bottom of the sump, goes to this tiny little pump, a little G-rotor pump, and then it squirts oil between the primary gear mesh here. But there's an oil seal here. And if you don't supply oil to that oil seal, because it's going 18,000 RPM, same as this one. And this is an HMBR seal. This is not a Teflon seal because it's got a seal. So that's supplied with a constant feed of oil. It's not great. It really doesn't need to be there. If this rotor area was just wet with oil, like the Model 3 is, then the seal goes away, everything gets better. But that's not how it is. So this pump was left in there. It still squirts at the gears, but doesn't really do anything. And it basically 100% of its usefulness is to lubricate and cool this seal. However, this oil there's no filter, there's no screen, there's nothing to keep it clean. So as metal particles from EIBD or whatever, differential shim wear, this oil just gets dirtier and dirtier. It doesn't help the way they manufactured it either, but that's a different story. Don't really want to go into the processes that Tesla used, but Let's just say that the oil was delivered to the customer not very clean on day one. One of the other flaws, which is not really going to rear its ugly head unless you're a really, spirited driver, is this bearing here is a 6208 deep groove ball bearing. And again, since the torque went from 380 to 725, this bearing ended up being undersized, plus RPM went up. Probably wouldn't have been a big deal, but in combination with this bearing being kind of undersized for the loads that are on it, it's also the one that's subject to bearing discharge. And there's actually a retention plate that holds that bearing in. So that bearing is, unlike this bearing cannot spin in the housing, which is good for not wearing the housing out, but it's bad for bearing life. And the reason for that is when this thing's under high load, it's always pushing in the same direction, right? So the load on the outer race is always in the same spot. Whereas if this thing could just migrate around, wherever it happened to be, it would always be in a different spot. And then the damage to the outer race would be kind of distributed along the entire circumference. But since it's retained rotationally, it's always in the same spot. So anytime this will spall a bearing, which is basically like a pothole in the bearing race, it's always in the same area. So it's not a big problem in the fact that your car's going to quit driving, but it is a problem. It makes a lot of noise, and you got to pull the whole thing apart, and then all the bearing debris has gone through everything a zillion times, squirted right into this gear mesh, blah blah blah. So it's not great. It's not a big problem. That's why it's down on the list. So differential shuttle is, let's go to this part of the screen. So some genius decided that they were going to press the bearing onto the differential here, and then press the bearing onto the differential here. And then when they put it in the drive unit, they had this little plate, little retainer plate, that was actually installed before this bearing was pressed on. And it has little screws that go through the housing, and then little seal nuts that go on the outside of there. So that basically constrains that bearing from moving in the housing. Great. We retained that bearing. Unfortunately, the axial load on this output gear is enormous. Many kilonewtons, let's just say. Plus it's fluctuating rotation, right? So expecting the press fit on the inside of this bearing to take that load is absurd, I guess is the right word. So what ends up happening is they were expecting that press fit to keep this differential centered, right? And so this bearing didn't clunk into here, but it didn't work. And so there was no shim in here. It was just like a millimeter of clearance or something like that. So once this thing starts sliding, it gets looser and looser, and then clunk, clunk, clunk. Every time you get on and off the throttle, this thing clunks back and forth. Again, doesn't fall out. It still transmits torque. It just makes a clunking noise. Shot peened gear. So this guy here is the input gear. In the early days, there was in all the days, I guess, there was a base unit and a performance unit. And this assembly was very similar, right? The rotor was the same, the stator was the same, all the gears were the same, right? The only difference was this gear was shot peened on the sport version and not shot peened on the base unit. And then when you put the inverter on, the inverter is very different on the base versus the sport. The sports have a red, more capable. There's a bunch of differences, but the easy way to tell is it has a red circuit board on the sport, and the base doesn't. But later, this gear was shot peened on all of them, so there was only one SKU number for this whole assembly. So, but this can break. This gear, if it's not shot peened, it can break. It's pretty rare, but spare drivers will break it. There's also a press fit on this gear and this gear. This is called the intermediate gear. So this gear is made, it goes all the way through this bearing bore. There's a diameter here, gear, another bearing bore. On the early ones, there was just a diameter here, and then this gear had a hole in it, and they just pressed them together. Unfortunately, they didn't have enough torque carrying capacity to transmit the torque. So they would slip. That's the bad news. The good news is they'd only slip once, and they would generate so much heat between that press fit that they would weld themselves together. How concentric they were when they welded themselves together is based on luck and when you let off the throttle and how long it spun. And so anyway, the later ones had a spline fit here. Again, this is not a big problem for the end user. You'll never know it. Your drive unit might be a little bit noisier, but LDUs are pretty quiet in general. So I doubt that's going to be too big of a concern. Another problem that these things had was the rotor on the original ones was brazed. So those probably have all been replaced because they had crappy splines on them too. But if it's an early one, it might have a brazed rotor. They fall apart, and yeah, they're just bad. The newer ones are electron beam welded, which still have some problems, but they're much better than the older ones. And the problems that they have, it won't result in a failure per se. It'll just reduce efficiency. So another problem, which is not too serious, is this bearing here, which is pressed onto the rotor. When it's installed, there's this stainless steel insert that's pressed and co-machined into the aluminum housing. But when this is dropped in, this has to just slide in, right? And so this slip fit here doesn't keep the bearing from rotating. And I don't know if anybody noticed this, but this is what's called a 4-bearing arrangement, right? And it's bearing here and here, 2 bearings for this gear, and then it has a bearing here and here, 2 bearings for the rotor. That was changed on Model 3 because of this situation, right? There's no possible way you can make this bearing and this bearing lined up with this bearing and this bearing. There's just too many pieces in the system and run out and position tolerances and stuff like that. So what ends up happening is this spline and this gear are fighting each other. And it's because it's off center and run out's not perfect and whatever. So what you get is this bearing is kind of, the force on it is traveling this way, this way, this way, this way, this way, this way in, 2 dimensions. So it's constantly trying to waller itself out. So what that does is it wears this stainless steel housing out. Some of the early ones had like little orange O-rings in here that did little to nothing except for make orange dust. So those were removed, but the later ones, they put Loctite in here to glue it to keep it from rotating, which lasts 6 months or something, and then it's broken. So it doesn't really, it causes a little bit of MVH, but you'd have to be really sensitive to notice it. What it does cause is this whole thing, the stator, this whole housing, this insert, in a reman world, if that's wallowed out, you can't reuse it, and that's an expensive piece. That casting is expensive, and the stator is expensive, so you have to throw the whole thing in the dumpster because of that stupid little whatever. So that's the only problem with that. It's a little bit of an MVH concern for the end user, but it's mostly a problem in service. Thanks for watching. If you like this content and want more, subscribe, like, and share.